And I'll go over just a few quick things and then we can get started. We're going to save the questions for the end. I'll moderate and feel free to raise your hand so I can unmute you and you can verbally ask a question. And I'll look at the question. If there's someone is confused, we'll make sure that question gets answered during the presentation. This is also being recorded, and this recording, along with some extra resources, will be shared later this week, hopefully before Friday. So we have three wonderful presenters with us today. Imari Walker, PhD candidate at Duke University. Kristin Holschbach, that's correct, right? Stewardship coordinator at Puget Soundkeeper, and Chris Wilke, global advocacy manager at Waterkeeper Alliance. So with that, I will turn it over to Imari to start the presentation.
Awesome, thank you, Gabby. Let me go ahead and actually go here first and click on share screen. Hold on, cancel this. Here. Okay. So, hi everyone. It's wonderful to be here today. I am Imari Walker. I'm going to talk about actually chemicals associated to plastic and microplastics and why they can be a concern for the environment and just us in general. And I'll just say again, I am in my 5th year at Duke. I research chemicals associated to plastic and microplastics in freshwater and in simulated bird and fish digests for stomachs. Alongside that, I am an environmental engineer, and I also spend a little bit of time in the law and policy clinic at Duke working on plastic policies. So I'm very passionate about this topic, and that's also why I ended up being a pretty engaged science communicator through my YouTube channel and through other opportunities like this. So the reason why we want to focus on at least some of the research surrounding microplastics and their environmental harm is because we are exponentially producing it, and it's going to take a really long time for it actually to degrade in our environment. For example, some of these items, especially these single-use plastic items in particular, can take years, decades to hundreds of years to actually degrade, whether that is as marine litter in our oceans and our lakes and our freshwater, to just being deposited on the road as terrestrial debris. And the reason why it takes so long for all of this plastic trash to degrade is because it needs to be exposed to the environment. And also it depends on the plastic type and what it's exposed to. So to actually degrade a plastic, you need exposure to water, which causes what's called hydrolysis to the surface of the plastic, exposure to air, which is called an oxidation of the plastic surface, or even sunlight, which is also known as photolysis, to mechanical abrasion, which is a bottle sitting on the shore being hit by waves over and over again that are grinding down that plastic. And throughout that time, while you're degrading it, you're making microplastics. And so I think the greatest example that I can think of is like that pool noodle that sits out all summer, and you can see it change colors, going, losing its color or turning white or yellow and brittle. You're seeing environmental degradation and transformation within a very short time span, just a summer. And those are the factors that affect the weathering of the polymer. They create cracks on the surface, and that's what allows microplastics to be released. And that's what the majority of microplastics are in our environment. They're known as secondary microplastics. And the other thing that we're concerned about is the chemicals that are associated to these plastics and these microplastics, because especially when you're a microplastic, you have larger surface area. And so it allows for a greater probability for it to be released, whether that's into water or air or whatever environment that it's located in. And so that is really determined by the chemical properties itself, or and the polymer, along with what it's exposed to, what kind of water it is, for it to reach first the plastic water boundary and then be released into water itself. So, to back up a little bit, we have to also think about like what kinds of chemicals are present in plastic. And a lot of them are based on aiding in the aesthetic of the plastic, like dyes and colorants, to aiding in the actual formation of the plastic, like plasticizers that make things flexible and shape and mold into whatever product we want, to things that allow for it to take so long to degrade. These things like antioxidants, UV inhibitors, even biocides that prevent microbial growth on the surface of your shampoo bottle. Those are chemical classes that are going to allow for those plastics to live for longer time spans in our environment. And they're not great because they are not physically bound to the polymer. They have every opportunity to actually leave and move into whatever matrices that they're located in. And some of these you don't actually want ending up in those places. A good example includes dibutyl phthalate. That's a well-known plasticizer in a lot of plastic types, especially used for like PVC pipes or water infrastructure. And another example is bisphenol A. I think a lot of people have seen BPA-free water bottles and other products that are now have BPF, BPS, BPG, go down the alphabet. There's tons of replacements, some better and some worse than the original substance that it's been replaced by. And there also includes chemical classes that are known as non-intentionally added substances. So these are things that, like in the name, they were not even meant to be added to the plastic, or they reacted with the plastic during the formation and are just present. And so there are tons of chemicals that are present in these plastics that have not been well characterized, and they have not been well looked at for their hazards. The examples of dibutyl phthalate and bisphenol A show that they are endocrine disruptors and potential carcinogens, but are still in use in a lot of our plastics. And then other examples for polymer additives can also be mutagenic, toxic to aquatic life, even persistent. I think people don't talk about this as much, but these perfluorinated chemicals that they're getting a lot of attention now are also known to be on plastic. They're known to be water resistant polymer additives, especially for these biodegradable compostable plastics, have thin films of perfluorinated compounds that are toxic and a problem for our environment. Another great example is with this study. They found over 3,000 chemicals that are likely associated to plastic packaging itself. And of those 3,000, they were able to only find a little bit of information about a lot of them. And at least 98 of them were shown to be potentially human health or environmental health hazards from these kinds of listed compounds themselves. So there's huge complexity with what you're going to get with each plastic product you encounter, and how much is present and whether those things are toxic or not. So it's a very difficult story to kind of wrap your mind around, because it's not a regulated thing. It's not very strongly regulated to know what's present and have public knowledge with what you're encountering every day. And the other problem is how are they released? What does it take? What environmental factors drive release of these compounds into water? An example I'm showing is just from my own work, is that things like temperature, and higher the temperature, the larger amount of release can be seen, and even pH, the pH of the water itself. The higher the pH, I was able to find more bisphenol A being released from these polycarbonate polymers. And then other factors like natural, like organic matter that's present in the water, did not have as much of effect, or UV light had differing effects on how much it can change, the polymer surface in the release of bisphenol A itself. And finally, so it's not just the compounds themselves that we have to worry about, like BPA being present in our water, but it's the transformation products. It's what happens when it ends up in our water? Can it change? What happens if it's in our air? What other pollutants can inform or influence the change in the compound? And my colleagues will talk more about this compound, but I wanted to highlight that there are transformations that can occur from things like this tire additive to these quinones, and they'll go more into the toxicity later. And then from other work that's been done is that when you look at plastic extracts from consumer products, like your yogurt cups or even other food contact materials, they found in studies that more than half of them induced some form of a toxic response, whether that was, oxidative stress or cell death, or even estrogenicity. And it really depended on the material type itself, especially for like these PVC, or polyurethanes, or even the biodegradable polylactic acid type polymer materials, showing that like even in the smallest concentrations, they can induce some form of a response. And even comparing around different kinds of responses, whether that is with effects with estrogenicity or anti-androgenicity, testosterone or estrogens, there are different responses by polymer type, and a lot of those compounds that they found in the extract were almost impossible to identify because they were either transformation products or they just weren't well characterized in the scientific literature. So there's just a lot of complexity to really understand and better define, especially for us researchers. So I'll bring it back to a little bit about what I do, and I'll actually share a little bit of my own research as well. So for my PhD, I'm focused on identifying compounds that are associated to various plastic types, including polymers that are commonly single-use plastics that would be found on the beach, to other plastics and microplastics in simulated freshwater environments, and even in simulated bird and fish stomachs, to see what compounds are readily released into these environments and how are they transforming when you age the polymer or when you expose them to different environmental scenarios like temperature and UV light, like I showed previously from my first chapter. So today I'm going to talk a little bit about my second chapter on studying polyurethane and polypropylene microplastics. So this is using what's called non-targeted analysis to really identify compounds that were not as well commonly identified and show their transformations and changes in our environment. So the objective of this work is first, to really understand what the fate of these two different polymer type microplastics were in a freshwater mesocosm, which is pictured on the right. And then two, what happens to the chemicals that are associated to these microplastics, and how are they changing and transforming over time? So the mesocosms are actually in the Duke forest, and they're 12 feet long, 3 feet deep, and they have just about everything in them from water, plants, sediment, snails, and anything else that wants to jump in it from the forest. But these boxes were dosed with both polypropylene and polyurethane in each individual boxes, and water samples were taken over 1 year. To complement this study, I also did an in-house laboratory controlled leaching experiment for about 3 months. And within the same plastic, I also pre-exposed it to UV light to age the microplastics ahead of time. So we had quite a bit of samples, including the water samples from the mesocosm and my own benchtop water samples, and extracts of the plastic itself to look for chemicals and try and identify some common trends over time. Analysis was done using our Orbitrap Fusion Lumos mass spectrometer, which allows us to get really strong mass accuracy, less than 1 part per million, and it gives us a really high critical resolution to really try and identify down to 6 decimal points the masses that are present within our samples. So we can get thousands and thousands of different features within samples and try and work to back work to actually identify them. And that's using multiple different softwares like Compound Discover or spectral libraries, along with in silico fragmentation tools. And for target standards, we use authentic standards themselves. But to quickly walk you through some of the identification, and that's usually using a spectral library match from like NIST, from their government database. We were able to find quite a few different features within the mesocosm and within the laboratory controlled studies, especially the fact that there was a lot more compounds present within the mesocosm than in the laboratory controlled studies. And there was a huge difference between polymer types, the number of compounds that were seen within each. And then when trying to find actual compounds that had library database matches, there were a lot fewer because there's just not as many compounds that are well studied in these libraries, especially transformation products. So one thing that we also were able to find was when comparing the extract of the plastic to the leachate of the plastic, there were compounds that were more likely to stay associated to the polymer, and a few of them were actually likely to migrate out into water. Secondly, there were different compound classes that were common to different plastic types, like these antioxidants, plasticizers, this UV inhibitor, to biocides and monomers of the actual polyurethane. And so for compounds of interest included, tinidin 770, which is a UV stabilizer, and a known long-term hazard to aquatic life. And within the polyurethane, it's the methylene diphenyl diisocyanate, which is used as a monomer for polyurethane and is a known allergen and respiratory sensitizer. So for the purpose of time, I'm just going to go through a little bit of the transformations of tinidin and then kind of finish it up there. So tinidin 770, like I said, is an aquatic life hazard. And when looking at the benchtop experiments, we were able to see that it was present throughout all 3 months of leaching. And over that time, it actually seemed to kind of decrease a little bit, and there was more present with UV light exposure. Now, one of the transformations that's possible with this compound, and also within the mesocosm itself, you could see that it's present for the first 3 months of the mesocosm water, and then it's no longer seen in the mesocosm itself, which could indicate loss of the compound or degradation by microbial growth, or even absorption of the compound to organic matter itself. But it's really hard to kind of piece that story together with so many environmental variables in a mesocosm. But another thing that can happen to tinidin itself is hydrolysis. And so that is a breaking of the ester group and forming this hydrolysis product. And what's really interesting is that this compound is 20 times higher presence for their area over that 3 months time. So this is actually the dominant structure within the water throughout that benchtop study. Another compound, and this is just the confidence that we have using in silico fragmentation tools. Another potential degradation of tinidin is actually hydrolysis followed by oxidation of the compound itself. And while this compound has never been seen in literature, it's what we propose with the structure and the matching of its mass spectral ion coverage. And it shows that with UV light, this is the only reason why it's present in these samples. So there's quite a few different transformations, and I'm going to see if there's quite a few different transformation products that can happen to just one compound itself that's commonly found, especially within this polypropylene. And you can see when you compare the mesocosm water to the actual benchtop studies, there's quite a bit less of it present per gram of polypropylene. And that's probably due to other factors like loss due to absorption or loss of the microplastics deeper into the water column. And it just really shows that even UV light has a pretty profound impact on the release of these compounds and a driver or even regulates the actual presence of certain compounds as well. So yeah, so I'll just kind of finish that up real quick. Just that polypropylene microplastics definitely demonstrated that they had more organic additives available to them than the polyurethane for this material in particular. And there were quite a few different compound classes that were present that were important and leachable within both of these microplastics. And finally, there was a trend of disappearance of these microplastics over time, especially within the mesocosm itself. And so that indicates that there are just different phenomena that you can see when doing a benchtop experiment versus actually doing an environmental study of these compounds. So general takeaways are that plastic contains quite a variety of different chemical additives, and those will aid in either the aesthetics, the functionality, or even the longevity of the plastic. Environmental exposure of these compounds or of these plastics can lead to release and transformation of these additives, along with the fact that some of these chemicals are, potentially toxic, have been shown in the literature, or just haven't been studied enough for their toxicity. And so I'm just finishing off just saying that we need further analysis to really understand the complexity of additives and chemicals within plastic and microplastics in our environment. And so big thanks to my laboratory, my funders, sponsors, and my research advisor, Lee Ferguson. And I will stop there so we can get to the next presentation.
Thank you so much, Imari. I believe, Chris, you're going next?
Nope, it's actually me.
And very close in name.
I know, so I was like, oh, awesome. I will share my screen then. Okay. And thumbs up if you can see my screen. Awesome, very cool. Okay, so I'm Kristin. I work with Puget Soundkeeper Alliance. We are a small nonprofit. We're based in Seattle, Washington. We are actually one of the founding members of Waterkeeper Alliance. I believe we were the 6th Waterkeeper. So our mission is to protect and preserve the waters of the Puget Sound. And so as stewardship coordinator, I organize a lot of our community, if not all, engagement events. So that's our beach cleanups, our pollution patrols via boats and kayaks, and then also a lot of our community science opportunities. One of them today I will be talking about is our microplastic analysis. And then Chris is going to be going after me talking a little bit about our salmon monitoring as well. So to dive in, I will be talking just about how we conduct these microplastic analysis. And then I'm going to talk about one specific location called the Green Duwamish Watershed, where we gather a lot of water samplings from. So just some quick definitions. When I was practicing, I realized I don't really say marine debris that much, but I kept it on. So if I do say marine debris, I am referring to manufactured solid materials that enter the marine environment. And then I will be saying microplastics, and that is plastics that are 5 millimeters across or smaller. And that definition is from NOAA. And we always like to tell our volunteers and the public to always think of like a little sesame seed. And that is kind of what we determine as a microplastic. So just some background information of how we got started with this project is we collaborated with Peter Hodem, who is a professor and a researcher at the University of Puget Sound. And so his primary research is microplastics and seabirds. And we wanted to start this program because working with Peter, he made it so community science friendly. He took what he does in the lab with his students and made it and adapted it so that we could do it in our office in Seattle. So no lab needed. And then we began these in about 2017, 2018 is when this was developed and implemented. So far what we found is we have done this at 72 different sites all around Puget Sound. But again, I'm going to focus on the Green Duwamish Watershed, which I will show you after this. And we primarily have like 30 to 35 sampling sites along this watershed. So on average, over 90% of our samples contain some type of microplastic. And when we do find a microplastic, over 90% have been filaments. And we have made an educated guess that it's probably from a lot of folks' clothing. A lot of it has polyester or it's made of plastic. So we believe it's from shedding. And then also maybe from boats with like ropes too, shedding off some of that material as well. So this is the Green Duwamish watershed, and this is what I've been talking about. So it is divided into 4 sub watersheds you can see on this map here. And we primarily gather a lot of our samples from the first 2. So this Puget Sound nearshore watershed, and then the Duwamish estuary subwatershed. Of course, we do grab samples in the middle Green River and the upper Green River, but those are more sporadic. It's definitely more condensed in the first 2. Since Soundkeeper does a lot of work on the Duwamish River, we have a lot of litigation. We do a lot of volunteer opportunities there and whatnot. And so just some more fun facts about this watershed is it is 93 miles long. It's also home to the most economically and ethnically diverse communities, and it provides habitat for 5 species of salmon that we have. So I did take these wonderful photos from my phone on a boat patrol. We do a lot of boat patrols on the Duwamish River looking for polluters. And then if we do find a polluter, we do report it and we do take legal action. So you can see it's very heavy industrialized. You can see there's a heavy machinery. You can even see in the right there, it's kind of faint, but there's some smoke coming off of that burning metal. So with that comes a lot of storm water pollution, a lot of when it rains, and rumor has it, it rains a lot in Seattle. When it rains, it picks up a lot of those toxins. And if these industries don't have proper stormwater treatment and water treatment facilities, it goes directly into the river. So that's where Soundkeeper has done a lot of its litigation on the river, is with stormwater treatment facilities. And then there's also the air pollution as well from these companies burning some of the metal and recycling and everything. So here, I'm a big infograph person, and I won't go too, you can kind of check this out, but you can see here, there's a lot of reasons that this area is polluted, specifically the Duwamish River. There's the stormwater runoff, the air deposition. Boeing is located right by this river as well. So a lot of that air pollution from the airplanes. Oil leaks, spill leaks, erosion and leaching. So I won't talk too much about this, but you get the picture that it's very polluted because of the industries. So now I'm going to go further into the demographic in this area in the Green Duwamish watershed. So I found some nifty maps. This map here, it shows percentage of population who are white alone, not Hispanic or Latino. So the blue is for areas where it is more white populations. And then the more like, I guess the lighter green, yellow is where it's less of a white population. So the Green Duwamish watershed, we're gonna start, this is Elliott Bay at the top here. The Duwamish River is the water that's flowing right under Elliott Bay. And you can see as you go down the Duwamish River, this area does turn into a less white populations. And you can also see that this is where the heavy industry, like the photo I showed you, this is where it takes part. So now my next map is going to show you the most common race among population of color. So again, this is Elliott Bay at the top. We're going down the Duwamish River, and you can see it's getting more into the green colors. And so that is Asian alone, and then also Hispanic or Latino communities. So it's very diverse, which is wonderful, but it's so unfortunate that there's such a heavy industry and I guess like industrial wealth in that community that's causing these communities to have a lot of pollution, air pollution, water pollution as well. And so that's why we do a majority of our water sampling on this river and in this watershed is to teach volunteers and the community just about this area and why it is so polluted and pretty much build clean water advocates, I would say. So now I'm going to go into how we do our microplastic analysis. So first thing you need to do is you need water in order to conduct these analyses. So we recruit volunteers to do water grab sampling, and we give them, it's so easy, we give them mason jars, as you can see in the photo, and we give them a map of their site, latitude and longitude as well, and a little data sheet. and then we send them off. Some sites are available by like foot and bus, but some sites you do need to go a little further out and you do need a vehicle to get there. But the volunteers are trained to rinse out their mason jars and disinfect it with the water that they're going to be using. And then on that third time, they secure their lid, write down the location, and then drop it off at our Puget Soundkeeper office or mail it to us as well. And we try to collect samples on the same day. Of course, it is a community science event, so it's never perfect, but we still like to try to get samples on the same day, so we are consistent with like the weather and everything. Okay, so here is a video I put together. Warning, it is not Oscar nominated quality. It's kind of fuzzy. So it might be a little hard to see, but I think you're gonna get the point across. There is no sound because I'm very good at creating movies, and instead I'm gonna talk over it. Another thing too is when I practice, I realize that the video goes a little bit quicker than how I talk, so bear with me, but it'll be fun, it's gonna be fun. Actually, I'm gonna make it big quick. Oh, don't look. Okay, 1 second. Okay. Okay, so here, this is Gillian, who's actually in the audience today, and she's our AmeriCorps volunteer coordinator. And so what we do first is we rinse our equipment with deionized water, and we also use distilled water too. And this is because there's dust, there's air follicles, there's everything. So we just kind of clean off everything. And then we pick one of our water samples and we simply measure out 150 milliliters, just like that. So pretty easy so far. And then afterwards, Gillian, she is going to be measuring out some hydrogen peroxide. It's 1 tablespoon, and she's going to put it on a hot plate with a magnetic stirring mechanism. And she's going to put that on for 15 minutes. And that's just to break down some of the organic material and dissolve it. Oh, there's the timer. And then afterwards, she's going to do the same thing, but she's going to put salt now in the water sample. And this is, again, it's to break down those organic materials further, but it also plays another part too, which I'll show you right here. So now she's pouring, now the sample's done, and she's gonna pour it into this funnel, and it's gonna sit overnight for 24 hours. And the salt is gonna settle, I don't know if you can see my mouse, but it's gonna settle in kind of like the tip, the bottom of that funnel. And so what we're hoping to happen is that the plastic is going to disperse and kind of stay in the water in the top of the funnel. And then the salt is going to pick up more organic material and settle in the bottom. So here she is now draining out the salt, and she's going to put the water over a filter to catch any microplastics we may have in this sample. And then she's going to put it over a petri dish that we drew like a grid system on to kind of keep track of where we are when we're under the microscope. And we are even going to get a bird's eye view of what we see in a or under the microscope too. Okay, so you can't see the microplastic, but there is a microplastic there. But in the next slide, I have it. I circled it, but again, you can't see it because of the quality, but I'll show you. So then we simply will mark it on our data sheet, and then we are done with our microplastic analysis. Of course, it does take, how do I get out of here? It does take longer than 2 minutes. It is a process, but that's just a quick spiel of how we do these. And you can see this is one of the microplastics we found when we did our water sampling recently, and it's a red fiber that we found. So we're assuming, again, it may be shed from somebody's clothing in the water or something. So that's that. And this is what we typically find. Again, like I stated before, we find 90% are filaments. We do find some pellets, but that's the most rare. And then we do find some fragments as well. But again, that's very rare. It's mainly those filaments we find. And so just to conclude on why we conduct these analyses is the educational value is extremely valuable. Again, it's teaching folks about the Green Duwamish watershed and also about microplastics. It's very community friendly, and it can get, you don't need to be a lab student or a researcher or anything to get involved with this scientific research. So it's very friendly to the community. It can help us inform new policy and also create advocates to learn about this issue more and do more for clean water. It's a unique volunteer opportunity as well. And then we can present this data. We collect data reports that we put online for the public too. And then we can use this information when we do our Duwamish Riverboat boat patrols and just spread awareness of this area more so and how it's polluted. But now I am going to kick it off to Chris, who is going to talk further about our community science, but he's going to dive into Longfellow Creek, which is in the Green Duwamish watershed, and talk about a little bit about our salmon monitoring. So I will stop sharing my screen.
Okay, I am having a hard time selecting my PowerPoint on the sharing screen. Hang on, apologize for that. Get this going here in a second. Okay, coming up. There we go. Sorry for the delay there, folks. Hi, everyone. I'm Chris Wilke. I am the Global Advocacy Manager at Waterkeeper Alliance, and we represent 350 plus Waterkeeper groups around the world. And before this job, I was actually Executive Director and Puget Soundkeeper at Puget Soundkeeper Alliance, and got to participate in some of that research. And actually, Kristin was, I think, the last person to come on board before I left. So we got to go on some kayak patrols together. That was great. And thanks so much, Kristin and Imari, for those wonderful presentations. I am going to go real short because I want to make sure that we have time for discussion. But I'm going to give you a real world example of some of the devastating impacts of microplastic pollution, take it out of the theory and show you what can really happen. Talk a little bit about community impacts and also a really important policy opportunity. I'm going to try to cram that into a very short period of time. So first of all, as we talked about before, there's a lot in plastic besides just the plastic itself. We know the plastic nurdles and fibers and fragments can have their own impact, but as Imari spoke on, there are many chemical impacts of this plastic. This is often very poorly understood. Just because there are harmful chemicals present in the plastic does not necessarily mean they're getting into the water, but many of them do. And thank you so much for that research, Imari. It's really important to understand which chemicals are more likely to enter the water column and what some of those impacts are. We also don't know necessarily what chemicals may result as a means of this pollution. For example, you start with one chemical, but then it becomes something else, which may be less harmful or it may be more harmful than the original. And how these compounds accumulate over time, and even synergistic impacts on marine life, for example, of two chemicals working together. This is often very poorly unknown. And for me, it just raises a much larger overarching question. Should we really be applying a precautionary principle before we introduce these products into the environment, into Mother Nature? Should we make the producers prove to us that they are safe instead of having to prove years later why are they harmful and why we need to remove them? It puts the burden on the wrong end of the spectrum, and we'll have more about that later. Let's see here. There we go. I'm going to talk a little bit about, as Imari hinted on, automobile tires. They are a significant source of plastic pollution. So it's not all just the single-use plastics, but it's estimated that tires are responsible for 5 to 10% of global plastic pollution in oceans, which is astounding, and up to 3 to 7% of particulate air pollution because of the tire. The way they wear, it becomes becomes dust and gets airborne. And also, of course, what goes up comes down, so it enters the environment. And we should not just be considering them rubber. They're less than 20% natural rubber, and in fact contain more synthetic rubber, which is a type of plastic, in the tires themselves. So when you turn in a set of tires at the end of their life, and they're a little bit smaller than they were, 24% of what you lost onto the road was in fact plastic. And what we're going to talk about now is the impacts of this additives to the rubber tires on one particular species of salmon. It's called the coho salmon. You may see it as a silver salmon on restaurant menus. All of our salmon have nicknames here. As Kristin mentioned, we have 5 different species. This is one of the more popular ones for sports fishing, for recreational fishing. And they hatch in small streams all along the Pacific coast, from California all the way up to Alaska, and I believe into Russia. They live for a year in small freshwater streams, and then they migrate out to sea, and they can migrate thousands of miles. Their migration route can leave the Pacific Northwest, where we are, and go all the way out to waters of Eastern Russia before they return. And when they return, they can be up to 20 pounds, more commonly 5 to 10 pounds. But they are very prized sports fish. And we've been participating in some monitoring of something called the urban runoff mortality syndrome, which this research has been led, very determined research by Washington State University, NOAA, National Marine Fisheries Service, and University of Washington. In particular, I'd like to recognize Dr. Jen McIntyre and Nat Schultz. I first found out about this studies they were doing in 2003. And what they were doing is they were documenting salmon that were entering freshwater streams that were dying before they spawned. And the marker for that is female salmon that have died and are still full of eggs. Because if you know much about salmon, they return to streams, they spawn, and then they die. So it's actually not unusual to see dead salmon along a stream, but they should not be full of eggs. That means they have not successfully spawned. And they are often, these dead fish are often ocean bright, which also, if you know a little bit about salmon, they change color when they enter freshwater as they become sexually mature and ready to spawn. They take on a different coloration. And these fish were returning and dying within hours. And Puget Soundkeeper participated in this research by monitoring this Longfellow Creek, which is the last tributary to the Duwamish River before it enters Puget Sound. It's right down there in the estuary, and it's a heavily populated area and is impacted heavily by stormwater. And the scientists studied the salmon for many years before understanding what the culprit actually was. And as it turns out, the coho salmon are very, very susceptible to this type of pollution. They wait to return to fresh water. They wait for the beginning of the fall rains. We actually have very dry summers here in the Pacific Northwest. It's beautiful. Don't tell anybody. But these fish are waiting for the creeks to rise. So they're waiting for these fall rains, and then they are getting hit with an entire summer's worth of pollution. All that tire dust over the summer is coming in all at once at the precise moment that the fish are entering the streams. And then also coho are susceptible because their behavior, they tend to prefer small streams, where other salmon species will spawn in the larger rivers and the main stem. The coho actually specialize in these small streams, which in an urban area, they can be more than 80% stormwater in these streams. And then their chemistry, they are uniquely susceptible to this pollution from a derivative of a chemical called 6-PPD, which is applied to tires as a preservative against ozone degradation to keep the tires from cracking. And so there's a safety element to this here, because it maintains the integrity of the tires. But very quickly upon entering the environment, it becomes 6-PPD quinone. I think I'm pronouncing that right. And thank you, Imari, for putting out the chemical formula earlier. You can refer back to that if you get a copy of this presentation. And that, at long last, just last December is when they finally published the research on this that showed it was this chemical that was causing the urban runoff mortality. And basically what happens is, at first, upon entering freshwater, the fish become disoriented. They experience a loss of equilibrium. They swim in circles. They're often at the surface. Now, these are fish that are very good at hiding from predators, so they're normally along the margins in deeper pools. These fish are completely lacking any level of caution. They're almost seemingly gasping for air at the surface. When you think about a fish that breathes water gasping for air, you can really understand something bad is happening to this fish. And they may, death may occur within hours. And in some years, 70, 80, up to 90% of these fish will die as a result of this syndrome, and which we now know after 18 years of research by Washington State University and University of Washington is because of tire dust and a specific additive that was placed in there. And I now want to show you a video, and like Kristin, I'm going to give you a warning, but this is a fish that is in the throes of the early stages of urban runoff mortality syndrome, and you can really see how tragic this is. You can see the fish is just, it's lost all its ability to maintain its equilibrium. You can see it almost gasping for air. It's just, it's really, really tragic. And the reason why I wanted to show you this video, I'll show you the next one too. This is a fish on a different day, but this is within, several hours, days after it's died. It's on the side of the river, and you can see this as a female that is full of eggs. This one's actually been had a necropsy done, which is why it's lying there with its belly cut open. This fish did not successfully spawn. And these fish lived their whole life in the ocean, came back ready to spawn, and they were unable to complete that journey because of plastic pollution, because of stormwater and plastic pollution. So it's really tragic. And the thing that I wanted to emphasize here is it is so rare that we actually get to witness these specific effects of a chemical. They often, it happens in the shadows. You don't see it happen. There's just, all of a sudden there's less fish than there used to be, and you're wondering what happened to them. In this case, the reason why we're able to keep observing it in this location is this is a, I'll stay here for a second. This is a small creek that's adjacent to a large river. So fish that are swimming up the Duwamish that are probably heading for other places, a certain percentage of them will stray. They'll take a right turn and head up Longfellow Creek. So if Longfellow Creek had to have a sustaining population of fish, they'd all be gone. There wouldn't be any left to observe. But because they are always seeking out to colonize new streams, a certain percentage of them, there's new recruits every year, and unfortunately, not many of them survive to spawn. So with that, I wanted to link to some of these articles here. This top one is the actual research. It's published by the University of Washington and Washington State University, as well as some other things that I've alluded to. And I just wanted to talk a little bit about the impacts of this. We're presented this really upon the survival of a species in urban environments in the Pacific Northwest. But I just wanted to pose this question: is this an environmental justice issue? Should we be looking at it through an environmental justice lens? And here are some of the impacts that happen when salmon are not able to return to spawn. First of all, impacts to tribal fishing rights and First Nations, where this may be observed up in Canada. The cultural importance of fish in the diet for many cultures. If it's not available, that is a severe impact. And as Kristin alluded to, these types of impacts are seen in communities with higher traffic, more pavement, more industry. And often recreational fishing may be very valued as an inexpensive source of protein in areas where sometimes you may have a food desert or other limited access to high quality nutrition. And then as for people that are interested in catching fish for its recreational value, affluent sports fishers don't have to fish in the local waters. They can travel distance to Alaska or to other exotic destinations to catch their fish. And in some cases, they may be the very owners of industry that are polluting their local streams. So that's another consideration. I really wanted to talk about solutions because we are limited on time. I'm going to go really quickly through this presentation because I want to make sure we have time for questions. We are running behind schedule, but this is a huge opportunity. This is something that is before us right now. It's been introduced into the US Congress, House of Representatives, and the Senate. It's the Break Free from Plastic Act. I think Alex Truelove, who is on our call, has been working hard on this with U.S. Public Interest Research Group. So thank you, Alex, for all of your work. This is very, very comprehensive legislation. I don't have time to go over this in detail. We've had other webinars about this, but there are here are some links where you can find out some more information. They took a lot of input and are really zeroing in on the producer responsibility and the systemic problem of plastic pollution. This is not about individual recycling behavior. And that's one thing that's really important to emphasize. There are different ways that you can get involved. You can sign on to support the organization. If you're an organization, have to sign on to support this legislation. As an individual, you can contact your legislator and ask them to endorse it, to move it forward. If you work for an NGO, you can share this opportunity with your constituency through an action alert, that kind of thing. And keep discussing the issue, whether it's on social media, letters to the editor. Of course, there's things that we all can do to refuse plastic in our lives and to work to reduce the amount of plastic that we take in. But just remember that recycling is really a broken system. Less than 8% of plastic is truly recycled. So the solutions do need to come much further upstream. And at the same time that we're doing this, we're also seeing the plastics industry and the petrochemical industry. This really is the plan B as the world transitions away from fossil fuels. They're trying to make us buy more and more plastic. So that's the reason we need to move forward here. So with that, I think we can stop sharing the screen and turn it over to discussion. Hopefully we still have some time. Thank you, everyone.
Thank you, Chris and Imari and Kristin. We don't have much time for questions, and but I want to remind everyone that you can either write them in the chat or raise your hand. We have a question from Michael. Michael, I don't know if you want to unmute yourself and just ask your question.
Yeah, I'm looking for a protocol where I can take large enough samples and then use some kind of density separation to start building the information we need to go after plastics bans. I mean, to me, the first thing to get rid of is the clamshells, the polystyrene stuff that degrades so fast. But we don't have a sturgeon story down here, but I think we do have a story with the chemicals that come off these plastics. But first, we need to know, to show somebody this is a problem everywhere. And I need data for my river.
I think I could answer that quick, and then Imari, I saw you just unmute yourself, so I'll let you take it too. But and I guess I'm not the best at this, but I don't know a standard protocol for sampling in the water column lore. Ours is definitely very easy and everything. But I do know there's a lot of universities and researchers who do have a way more in-depth system. So I could try to get your email, or you could put it in the chat, and I can email you folks who I think would have better knowledge of doing a more advanced like water sampling and protocol.
Thank you.
Mm-hmm.
Yeah, I was going to add that I know Jenna Jambak, I believe she has some things on her website about sampling, and I believe Max Liberon, it also has one as well. So I can put those links to their websites. I think they have some resources for that in the chat.
Well, I don't see any more questions for now.
I'll just add to Michael's question, because he also sent me a question in the chat, that this Break Free from Plastics Act really is the best opportunity in a generation to start to deal with this proliferation of plastics that we find ourselves in. So I would just encourage you to take a strong look at that, sharing it with your constituency, Michael. We really need people in swing districts to push for this, to get enough momentum in Congress to pass this. We obviously would like to see it all passed as a package, but sometimes even pieces of things can be moved along later. And if you want anyone who wants to coordinate further on this, I should feel free to contact me at Waterkeeper Alliance, or I'm just going to put in a plug for Alex again. Alex Truelove at US PIRG is working hard on this as well. There's lots of opportunities to get involved to push this forward. And the monitoring is really important because it shows us what's actually happening in the environment, the accumulation of microplastics, the leaching of the chemicals, the real world examples of fish dying. Where we have that information, we should use that to couple that with the policy solutions that we are talking about.
Sadly, Chris, I'm in one of these red states where our legislature is busy banning municipalities from banning plastics and that sort of thing. So that's why I'm interested in getting the data, so we can go to our fishermen, we can go to local municipalities and maybe get them to push back against the legislature. Yeah. While we do the same thing.
And I believe in this legislation, Alex, you can correct me if I'm wrong here, but is there a ban on bans in this legislation? Is that part of what we are talking about here?
Hey everybody, this is Alex. I don't think there's a way to legally prevent states from instituting their own local preemption, but there is no federal preemption of state actions. So in other words, if this federal bill would pass, it would not keep any state from going further individually of their own laws. And I think there's also language in there to sort of reward states financially through the grant programs and things in that bill if they don't have preemptions. In other words, if you're a state like Michael, where you live in, I'm not sure what state it is, but if you lived in a state where there's preemption, those states wouldn't get the same resources as states that do. So there's a little bit of a carrot there. Legally, I don't think federally you can repeal statewide preemption, but it allows for state flexibility, if that makes sense.
Thanks, Alex.
Thank you.
Are there any other questions?
Looks like we have some comments, a bunch of thank yous, and I'll be sending this recording and this presenter slides and some of the links that Chris shared, and feel free to send me anything you think is pertinent to this conversation. I can share it with the group. But it's just past the hour and it seems like we don't have any more questions for now. So I want to thank the presenters and thank you all for joining us today.
Thank you all.
Thanks, everyone.
Thank you.
Thanks for doing this. Thank you.
Of course.
Very much.